Good afternoon, everyone. My name is Shankar Kumarja, and today we are Tuhin Datta and Naveen Khare. We are from the Indian Institute of Technology, Patna. Today, we will be presenting a comparative analysis of the three different approaches: greedy genetic algorithm and constant programming for solving the electrical vehicle routing problem, or EVRP. So, statement. So, what exactly is the problem we are tackling? So, imagine a city network with a central depot and several customers' location needing pickups and deliveries. So, we have a fleet of identical electrical vehicles, each with limits on how much weight they can carry W and how much energy they store E. So the key challenge is efficiently routing these EV, considering that energy consumption depends on distance and the weight carried, alpha into D into W. Furthermore, EVs must contain a minimum charge level currently set at 15% and need to potential recharge at station with limited port and constant charging rates. Finding the best routes under these conditions is the core of EVRP. So these are the diagrams of our problem statement, and these are our objectives, and these are the problem setups. So assumption, what the assumption we have made for this problem. So to solve this complex problem, we explored three distinct methodology. The first one we will discuss is the greedy heuristic. As the name suggests, this strategy builds route step by steps, always making the locally optimal choice at each stage based on the energy efficiency while respecting the vehicle's constant. So let's look at how it works. The process start with all EV at the depot fully charged and empty. At each step, the algorithm looks for the nearest customer that the EV can actually serve, meaning it has enough energy to get there and back, or to add a charger, and enough capacity for the pickup or delivery. So when choosing between multiple feasible options, so it prioritizes customers with larger demand and those that require less of a detour from an efficient path. So before assigning a node, the algorithm performs crucial feasibility checks. It ensures the vehicle's weight capacity won't be exceeded after the pickup or delivery. It also calculates the estimated energy needed using the formula alpha into D into W, and confirms the vehicles will maintain at least 15% charge upon arrival. So, if the energy level is predicted to drop below this threshold during its route, the algorithm reactively inserts a trip to the nearest available charging station. So this is the process of selecting the best next node, checking feasibility, and inserting charging stops. Continue iteratively until all customer demands have been met and all vehicles have returned to the depot. So the primary goal, the optimization of objective for this greedy approach is simply to minimize the total energy consumed across all vehicles. So what are the takeaway from the greedy approach? So its main strength are simplicity and speeds, and it's easy to understand and execute quickly, making it potentially useful for smaller problems or real-time adjustment. However, its major drawback is that by only looking at the immediate best steps, it often leads to the suboptimal overall routes and doesn't consider the global structure of the problem effectively. So now Tuhin will introduce a more sophisticated approach, the genetic algorithm. So now it's time to over to you, Tuhin.
Thanks, Shankar. The second method we explored is the genetic algorithm, or GA. Unlike the step-by-step greedy approach, GA is a meta-heuristic inspired by natural evolution. It works with a population of potential solutions, entire routing plans, and iteratively improves them over generations to find near optimal results, primarily focusing on minimizing energy consumption. To use GA, we first need a way to represent a solution. We encode each potential solution, called a chromosome, as a set of routes, one for each vehicle, detailed the ordered sequence of customer visits. The process begins by generating an initial population of these chromosomes, often using simpler heuristics or random assignments, ensuring these initial solutions are feasible. The core of the GA lies in its evolutionary operators. First, each solution or chromosome in the population is evaluated using a fitness function, which in our case primarily measures the total energy consumed. Lower energy means higher fitness. Then, parent chromosomes are selected based on their fitness, often using methods like roulette, wheel, or tournament selection, giving better solutions a higher chance of reproducing. Next comes crossover, where segments of roots are exchanged between two parent chromosomes to create offspring, hopefully combining good characteristics while maintaining feasibility. Finally, mutation introduces small random changes like swapping customer visits or reversing part of a route to maintain diversity and prevent premature convergence. An important aspect is handling charging. This might be done by post-processing each generated route to strategically insert optimal charging stops and decide on the amount of energy to recharge. The GA continues evolving the population through selection, crossover, and mutation for a predetermined number of generations, or until the solutions stop improving significantly. The main objective, similar to the greedy method, is to minimize total energy consumption. But GA can also be adapted to consider secondary objectives like minimizing travel time or distance. For our implementation, we used specific parameters to guide the evolution. A population size of 50 solutions running for 100 generations with a mutation rate of 0.1 or 10%. The fitness was directly calculated based on the total energy consumed for each potential routing plan. These parameters influence how effectively the GA explores the solution space. The genetic algorithm or GA offers significant advantages. It can effectively explore very large and complex search spaces and is flexible enough to handle multiple objectives. However, it can be computationally slower to converge compared to simpler heuristics, and there is no guarantee that it will find the absolute best global optimum solution, as it might get stuck in a good but not perfect local optimum. Next, Naveen will discuss our third approach, constraint programming, which aims for optimality. Naveen, please take us through the constraint programming approach. Thank you.
Thank you, Tohin. Our third approach is constant programming or CSP. Unlike heuristics or meta heuristics, CSP aims to find a probably optimal or near optimal solution by modeling the program mathematically. It involves defining variables, their possible values, domains, and the rules they must satisfy. The solver then systematically searches for a valid routing plan that meets all constraints. In our EVRP model using CSP, the key constraints are ensuring the vehicle's weight capacity, that is W, is never exceeded, maintaining the energy level above the 15% threshold, respecting the limited number of ports M at charging stations, and fulfilling all customer pickup and delivery demands exactly once. We also enforce that each vehicle starts and ends its route at the depot. The objective function we aim to minimize is again the total energy consumed across the fleet. Um, to implement this, we utilize the OR tools routing server, a powerful library specifically designed for vehicle routing. The other combinatorial optimization problems using constraint programming. The solver generates routes that inherently respect all the defined constraints. Energy consumption is dynamically tracked throughout the potential routes using a callback function that considers the vehicle's load, the distance traveled, and the energy consumption factor alpha. The main advantage of CSP is its ability to find optimal or near optimal solutions, specifically for small to medium sized problem instances. It rigorously enforces all constraints. However, accurately modeling complex real-world problems using CSP can be challenging, and the approach often doesn't scale very well to very large instances, meaning the computation time can become prohibitive. Now let's compare the performance. This table summarizes key metrics in terms of runtime. The greedy heuristic is the fastest. GA, that is genetic algorithm, is moderate, while CSP can be slow. For route efficiency and minimizing energy usage, CSP performs best, optimal or near optimal. GA is competitive, near optimal, while the heuristic is often suboptimal. CSP guarantees feasibility if a solution exists, whereas the heuristic might not, and GA relies on tuning its fitness function. Looking at broader features, CSP provides high accuracy but has limited scalability and moderate speed. The heuristic is very fast and highly scalable but offers lower accuracy and weak constant enforcement. GA provides a good balance, medium to light accuracy, moderate speed, and high scalability, and it's highly customizable through its fitness function and parameters. The best use case depends on the specific needs. CSP for smaller problems needing optimality, heuristics for quick approximations, and GA for larger, complex EVRPs. Looking ahead, there are several avenues for future work. This could include incorporating time windows for deliveries, dynamic traffic conditions, battery degradation models, or even developing hybrid approaches that combine the strengths of these different methods. In conclusion, we compared greedy genetic algorithm and constant programming approaches for the electric vehicle routing problem. Each method has distinct strengths and weaknesses regarding speed, optimality, and scalability. The choice depends heavily on the specific requirements of the application. Thank you for your attention.